Hello, we're going to go over AP Chemistry, Chapter 3, Section 8, Formula Mass and Molar Mass. We're going to be calculating the number of atoms or molecules in a sample. So basically we're converting between moles, grams, and atoms using compounds. So as an analogy, here we have 4 jars filled with different amounts of coins, and we're given the fact that 10 pennies weighs 27.5 grams. So this is like analogous to having 1 mole as our amount, weighing a specific amount of grams of each element. And we're going to be able to calculate how many pennies are in here, just like we could calculate how many atoms or how many moles we have given the molar mass. Okay, so we're going to use dimensional analysis, which remember is just a fancy way of saying we're canceling out the units to convert from one unit to another. So for jar B, we started with this mass of 409.75 grams. That's how much this jar weighs in grams. Okay, and we're going to use our conversion factor here with grams on the bottom and number of pennies on the top. And you can see the grams have canceled out. So we have 409.75 grams total. 10 pennies on top, because we want pennies at the end, weighs 27.50 grams. So we divide 409.75 divided by 27.5 and then multiply by 10, and we should get 149 pennies. The same thing is done for jar D. So jar D, you can tell, is much more full, and it has a mass of 2,623.50 grams. So same conversion, except this time we have 954 pennies. Okay, as an aside here, this is something I want you guys to work out or at least think about, because it's going to come back down the road. So jar B appears to have these impurities in there. We have some quarters where the pennies are supposed to be. How would this affect the overall mass of your jar? How is that going to affect the calculations in your number of pennies in jar B? Given the mass of 10 quarters is 56.7 grams, so if you know the mass of the quarters and you know that there are quarters in here, and the fact that there are 100 total coins, how would you calculate the number of quarters in the jar? Okay, so this is like a bonus question, but this is going to be something that comes up later when we have a mixture of different compounds and we're trying to figure out how much of the impurity there is. Okay, so formula mass is the mass of a single molecule or a unit. So for ionic compounds, like NaCl, 1 unit would be the formula mass. Molar mass is the mass of an entire mole of those molecules or units, and it's in grams. So numerically, these are the exact same thing. We add up the masses found on the periodic table. The only thing different is the units. So one is AMU and one is in grams. Let's do some examples. Find the molar mass of H2O. So H2O is going to be, let me present the slide so I can write on it. So H2O is going to have 2 water molecules. So we have 2 times 1.01 grams. Okay, that's a 1. Plus, we have our 1 oxygen, which is 16.00 grams. Should be grams per mole. Sorry about that. And so when we add them up, we're going to get 18.02 grams per mole. And I just did that correctly, but this says formula mass, so that tricked me. Over here, I found grams per mole. It's actually going to be atomic mass units for the formula mass. I was just seeing if you guys were paying attention. Okay, and then down here it says find the molar mass. So if I were to do the whole thing over again, I would get the exact same answer, but this time it would be in grams per mole. So numerically, the formula mass and molar mass for water is 18.02. For the formula mass, it's going to be in atomic mass units, because we're talking about one single little water molecule. Okay, what is the mass of that? It's 18.02. Oh, I don't know how that disappeared. 18.02 grams. 18.02 AMU. And if we have a whole mole of those molecules, it's going to be 18.02 grams. Okay, so here's a really long problem that explains how to use dimensional analysis to go from, in this case, milligrams. They threw in that extra little bit. They threw in the extra little bit of, instead of grams, they gave us milligrams. And we want to know how many molecules there are. So we are going to go from milligrams to grams, grams to moles, that's the molar mass part, and then moles to molecules. So a lot of steps here, and that's why it's such a long problem. But if we write out our given and our given units, we'll see that it's not so hard of a problem. We start with milligrams, and we need to change that to grams. So we put milligrams on the bottom, so the units that are given are the ones that go on the bottom. We're trying to change to grams, so they go on top. So milligrams have canceled. Okay, and now grams need to cancel, so we're going to put grams and moles. This is the molar mass, and it's already been added up for us, but normally we have to add up all of these atoms to find the molar mass, and it's 180.5. Grams are going to cancel, and then we have moles, but we want molecules. So an easy way to go from moles to molecules is with Avogadro's number. Moles will cancel. 1 mole is always Avogadro's number of molecules. So we do 325 times 1, which is the same number, times Avogadro's number, and then we're going to divide that by 1,000, hit enter, and divide by 180.15, and we should get this value right here, 1.09 times 10 to the 21st molecules of aspirin. Okay, so for practice, I want you guys to try the for practice, and we'll go over it in a minute. All right, so same type of problem. We are trying to go from milligrams to molecules, so we have all of these steps to do. So start with our 200.0 milligrams over 1, and I'm just going to write IB for ibuprofen. It looks like pounds. There we go, IB, so I don't have to write out the long formula. And milligrams need to go away, so milligrams go down here, grams go up here. 1 gram has 1,000 milligrams, and now we have converted it to grams, so I want grams to go away so I can get to the what we're being asked for, molecules, and I can change from grams to moles. 1 mole of ibuprofen, okay, now we are going to have to add this up, so we would have, oh, what in the world is this? Sorry about that, this is confusing, I don't know how that got there. Ignore. Here's our ibuprofen over here. Okay, so we have 13 carbons. So 13 times 12.01 plus 18 times 1.01. That's the mass of hydrogen. And I'm getting these from the periodic table. And 2 times 16.00. So if I add up all of those things, I should get a really big number that I don't have written down. Okay, let's do it. So we have clear, 2 times 16 is 32, and 18 times 1.01 is 18.18. So I just need to do 13 times 12.01 equals, okay, and then add my 18.18 for the hydrogens, and add my 32 for the oxygens, and it's 206.31. All right. To 6.31 grams, and then last but not least, now that grams have canceled, I need moles to cancel. 1 mole is always Avogadro's number of molecules. Molecules of ibuprofen. Okay, and I am going to cancel out some zeros here before I do my calculating. So this 0 and this 0 can cancel here, and I think that's it. So I have 2 divided by 10 times Avogadro's number and then divided by 206. Okay. All right. No. No. Okay, we're going to have to reopen that. Let's see if I can calculate while it's pulling it back up. Phew. Okay, 2 divided by 10. And I'm going to do divided by 206.31 equals, okay, times 6.022 exponent 23, enter. Okay, did not give it to us in scientific notation. 5.84 times 10 to the 3, 6, 9, 12, 15, 18, 19, 20. 5.84 times 10 to the 20th. All right, there is our answer. So that's how we convert from milligrams to molecules. All right, so section 3.9 is composition of compounds. We have mass percent, which is any percent is a part over the total times 100. And so we are going to have a part like this, 70.9, over the total mass times 100. Okay, and so for this problem, it's done for us. What percent of chlorine is in the CFC? That stands for chlorofluorocarbons. These are the ones that eat holes in the ozone layer. Cl2, F2. So first we find the molar mass of our compound. So we're going to add up our carbon, our 2 chlorines, and our 2 fluorines and add them all up. Okay, so this is our total molar mass of the whole thing. This is just the mass of the chlorines. Okay, the chlorines that were in there weigh 70.9 grams. So we put the 70.9 over the total times 100. It's 58.64% chlorine. They could have asked us for the percent carbon and the percent fluorine, and we would just take the parts of them and put it over the total, like 12.01 over 120.91 times 100, but it didn't ask for that. Okay, so we're not going to do those. Example 3.14 says calculate the mass percent. So we're going to have a fraction here, right? That leads us to our percentage of chlorine in the refrigerant Freon 112. So it's C2Cl4F2. And this is on page 110 in your textbook. I'm going to give you guys a minute to try this problem. Okay, so we have to start by adding up the molar mass. So for this compound, I'm going to write it up here. We have 2 times 12.01. We have 4 times 35.45. And we have 2 fluorines, so 2 times 19.00. We add all of that up, and we're going to get the total mass of this guy, which is 203.8 grams per mole. Okay, that's the total molar mass. Okay, I'm double checking it again, and that looks correct. Okay, so we're just worried about chlorine again this time. So this 4, we have to know what this part was, and the 4 chlorines had a total mass of 141.8 grams per mole. Okay, so we're going to take the part that came from chlorine, divide it by the total mass of 203.8 grams per mole. Notice that these cancel, so percentages, they don't have any units. Times 100 And the answer should have been 69.58%. And for these mass percent problems, it's typical that we have 2 decimal places. So it's sometimes 1, but usually 2 decimal places for the percent compositions. Since we're adding up the molar masses, and the molar masses have 2 decimals, that's usually where we round them to. Our answer has 2 decimal places. Okay, so how do we use those mass percentages to convert? And this is actually a really handy shortcut in problems. So we'll use this a lot in the multiple choice sections. We'll see some example problems of that next week. So the question might say, like this one does, how many grams of chlorine are in a kilogram of our CFC here? So we're going to use the fact that we just found the percentage. Remember, we did this problem. So it was, this is not written, but it should be 58.64. And usually the question will tell you, or you can calculate it like we just did really quickly. 58.64% chlorine in CCl2F2. Okay, so that is our percent composition. And what the percentage means, remember, is that we have this many grams of chlorine in 100 grams total of our compound. Or we can write the inverse of that and still have it be true. It's just like 12 inches over 1 foot is equally correct as 1 foot is 12 inches. We can use either one of these to convert. We can use either one of these to convert in our problem. So we're given a kilogram, so we write the given. We need grams, so we're going to divide by kilograms. So these cancel. There's 1,000 grams in 1 kilogram. Okay, and then we need grams to go away. So we're going to put, and we should have carried on this. So this is grams of what? CCl2F2. Sorry about that. Okay, CCl2F2 is what we're talking about. So we want that on the bottom. So in here, we want this one on the bottom, and we're trying to find chlorine. So chlorine goes on top. So we're going to use this conversion factor. And then we can cancel some zeros here. Okay, so we have 1 times 10, which is 10, and 10 times this value gives us 5.86 times 10 to the second, or we could have just moved the decimal 1 place over and called it 586.4 grams. All right, let's do some examples. Go ahead and try example 3.15. It's on page 111 if you want to look at the problem there. You can do that, and you can do it digitally or you can do it in your notebook. All right, so we want to know if 2.4 grams of sodium we need to consume less than 2.4 grams of sodium per day. What mass of sodium chloride, so we're changing from Na to NaCl in grams, can you consume and still be within that guideline? So now they're very nice here. See, they told us the percentage, so we don't have to calculate the mass percent of sodium in sodium chloride. They already did that for us. Okay, and so it's just an easy one-step problem. Put this over 1. I need grams of Na on the bottom and grams of NaCl on the top because it wants to know what mass, that's grams, of sodium chloride can we eat. So we just said percentages, that's 39 NAs in 100 NaCls. Okay, so 2.4 times 100 divided by 39, and we should get 6.2 grams of NaCl, which your book tells us is equivalent to 12 packets of salt. So we want to eat less than 12 packets of salt per day. All right, next, try for practice 316. Okay. So we're going to start with our mass of aluminum sulfate. Okay, and it's important to write out our formulas here so we keep the oxygen and the aluminum sulfate separate. Okay. And I don't have this one added up, so we're going to have to add this up. We got some work to do. 2 times aluminum. Aluminum's mass is 26.98. Grams per mole, plus we have 3 sulfurs, and sulfur's mass is 32.06, plus we have 3 times 4, we have 12 oxygens, and each oxygen has a mass of 16. So this is going to be a big molecule, and let's go ahead and add that up. Keep. So we have 26.98 times 2 equals 53.96. Let me write. I have to go back to percent. Darn, this is going to be a pain in the behind. Keep. I forgot the number, guys. 53.96. Okay, plus 3 times 32. Which is 96. And 12 times 16. Which is 192. Okay, so let's add those together. So that's 96 plus 192. I just ran and grabbed my cell phone, so I'm using that. Okay. All right, so this is my total. I have 53.96 grams per mole over our total, 341.96 times 100 to find the percentage. 53.96 divided by 341.96 times 100. It is 15.78%. Okay, so believe it or not, that's going to make our calculations easier over here. Okay, so in 100 grams of my aluminum sulfate, I have 15.78 grams of, oh, I did aluminum and it says oxygen. Oh, that's the worst. Okay. I'm just going to keep going with it. Of aluminum, let's see what that gets us. 15.78 times 7.2 divided by 100. I really need you guys here to keep me in line. I get sidetracked very easily. 1.14 grams of aluminum. Okay, let's redo the problem with our oxygen. So the mass of oxygen that's in there, and there was this 12 oxygens, so this was the 90, no, this was the 192. 192 over 341.96. Let's see what percent was oxygen. Times 100. It's 56.15. Okay, so same problem, but now we are going to, let me erase that really quick and change that to our oxygen. Okay, there we go. So we have 56.15 grams of oxygen, and let's erase this. Okay, and change that back. All right, so different problem, 7.2 times 56.15 divided by 100 is 4.04 grams of oxygen. So in a 7.2 gram sample, we have 4.04 grams of our oxygen. Whew, that was a lot of work. All right, and that is it for section 3.8 and 3.9. Have a great day, guys.